As we did with linear translation, in rotational motion we have constant acceleration, and when you have constant acceleration you have the constant acceleration equations, but now we have to make sure we can write them in terms of rotational. So we have the first one we can write is that the final angular velocity equals the initial angular velocity plus angular acceleration times time. Notice that this used to be d final equals b initial plus at. We have omega final squared equals omega initial squared plus 2 alpha theta final minus theta initial. And then the last one we have is that theta final equals theta initial plus omega initial t plus 1/2 alpha t squared. So these are the equations that we've had previously, but now we're using them for rotational motion. And if we look at the first part for the next problem, it says what is the angular velocity after 3 seconds. So we're looking for final angular velocity, and a quick inspection of what we have, we notice that we can use this equation to solve it directly. We're told that initially it's at 27.5 radians per second. It's accelerating at a rate of minus 10 radians per second squared, and it's accelerating at that rate for 0.300 seconds. So this gives us about 24.5 radians per second after that time. Part B is asking for how many rotations or revolutions that happen, so we can use theta final equals theta initial plus omega initial t plus 1/2 alpha t squared. And if we plug in what we know, like we did before, we can assume we start the revolutions from some reference point 0. Initially we were rotating at 27.5 radians per second. We took 0.3 seconds to rotate. We took 0.300 seconds before we stopped. 1/2 the acceleration rate times the time squared. Again, we do this, we get a final angle of about 7.80 radians. And since we're asked for how many revolutions that is, we can say that radians is the same as, if I multiply that by 1 revolution for every 2 pi radians, I get about 1.24 revolutions.